Hello, welcome. We are going to work a problem together from the in-class notes. This video is made assuming that you have already mastered one-dimensional motion and that you have been introduced to two-dimensional motion in class, both the equations and the concepts. The best way to use this video is to watch and pause at certain points and see if you can answer the question yourself. The video is very similar to how we work problems in class. I will lead you to a point and then I'll ask you to think about what comes next. Please pause the video and do that good thinking. It will speed up your mastery of the material. If you come back from having decided on what you think the answer is and play the video again and it turns out you got it right, fabulous, proceed. If you did not get it correct, then I would ask, go ahead and watch the rest of the video, but make a note of it and follow up with me or your lab instructor or your tutor because questions like this can really help us to learn and master physics faster. It could be your idea was a completely fabulous one that was just another way to solve the problem. Recall, many of the problems that we work will have more than one correct route or answer. Or it could be that you have a concept or equation misunderstanding, and that's learning. And if we can sort it out, then the next time you encounter it, you'll get it right. All right, so this problem comes from our Motion in Two Dimensions projectiles packet. And as I said a moment ago, it assumes that you've seen all of this information before and that we've labeled those equations. So we're going to move to the punter kicking a football problem, and we're going to write down our givens. And so typically people start by writing down the things that are numbers. The numbers are definitely going to be a given. And so I'm told that it's punted at an angle of 30 degrees. And so I'm going to draw a picture and write down that 30 degrees with respect to the horizontal. So there is the theta that they gave me. And the next thing I come across is a speed, and it's that initial speed of 20 meters per second. So I'm going to write that down. And then I'm going to focus on what I am told that we're looking for. Where should the punt returner position himself to catch the ball just before it strikes the ground? That is often referred to as the range, and in terms of our equations, what is that? Hey, if you said delta x, you got it right. All right, our next step, I have a couple of things I could do next. And what I'm going to do is the origin. I'm going to draw myself an x and y axes and place it. Where do you think that I should place the origin of the Cartesian coordinate system? All right, so that one was a little bit tricky. The correct answer is anywhere. You can put the origin anywhere you want. And as long as you're consistent throughout the problem, you should get the exact same answer, no matter where the origin is located. However, it's often to our benefit to put the origin somewhere that is a start or an end spot. So I'm going to put mine where the football begins, its trajectory. And I'm going to label what I'm looking for here. That delta x, I'm showing it in my picture. So the green there is the path. The green highlighter is the path that the football is going to take. And now this brings something up. Delta y. What is delta y? We know that delta y is 0 meters because the ball is kicked and caught at the exact same height. Its change in y is 0. All right, so what else do we not know? There are hidden things. They're not stated in the problem, but they're things that we know because this is a projectile. What are they? I hope that you said the accelerations in both the x and y directions, because in the y direction, it is always going to be negative 9.8 meters per second squared. And in the x direction, as long as we don't have wind or a thrust of a engine or something like that, the acceleration in the x direction will always be 0. And a good early step, but doesn't have to be done here, is to take your v naught and your theta and calculate your initial velocities in both the x and y directions. So that's what I'm doing here, is I'm using my right triangle and my definitions of cosine and sine, and I am calculating what the initial velocity is in the x direction and the initial velocity in the y direction. And that's just because I know I'm going to be needing that, because I'm familiar with those formulas, the kinematic equations that we covered last time. Those don't have any v naughts in them, only v naught x and v naught y. All right, since we're looking for delta x, we want to ask ourselves, which equation should we use to solve for the range, or the change in x displacement? All right, so I hope that you picked B. I hope that you picked B. The ones on the right don't have delta x in them, so it has to be one of the ones that's on the left there, and B is the one that we're going to use. And if we look at what AX is there, which we wrote down when we were organizing ourselves, AX is 0. So that last term will be 0. So my equation B becomes a little simpler. I just have delta x equals v naught x times time. And hey, we already got v naught x up above. We already did that. So now what we need is to find time. All right, so how are we going to get time? Let's hop up and look at what we have. What do we know from our givens that we haven't used so far? So I hope that you selected E. E is going to allow us to solve for time. So I'm going to write out that equation, sub in everything that I know, use that to solve for time, and that is my time of flight for this football. Okay, so we're ready for our last step. I'm going to take that time that I just solved for and substitute it in to the delta x equals v naught x times t equation. So the v naught x I had from earlier, I'm going to use that time, sub it in, and I will have how far my football went, so where the punt returner should position himself to catch the ball.